Okay, so for this problem, it's problem 19 in Goldstein's classical mechanics book. Um, it says, it's problem 19, it says obtain the Lagrange equations of motion for a spherical pendulum. So that is a point mass suspended by a rigid weightless rod. So it's just like a normal pendulum problem, except now it's in 3 dimensions. So we're going to draw it so we can sort of make sense of it. So we have this is the, ceiling that it's suspended by, and it comes out. And if we're looking at it from the side, then this here would be our z-axis here. This is our z-axis, and the weightless rod with, you know, with a point mass in the end m. The weightless rod has a length L, and then it's coming away from the z-axis at some angle theta, and then this length here will be L sine theta, and then this length here is L cosine of theta, and then this length here is what matters, I think, because when you're thinking about these problems, you want to think about potential being the lowest if this rod is straight down, where theta equals 0, right? And then that way it just makes the length. Because if we have, if we have our potential, so let's just write that down really quick. So our potential is mgz, right? And so if it's at our lowest, then we have it when it's straight down. So this distance here, the smaller distance, is L minus L cosine theta. So it's the full length minus the length, the partial length that it extends to. So this is also written as L1 minus cosine theta. And this is going to be what's really important for what z is. That is our z, because this is our potential, so it's going from the bottom up. Okay. Anyway, so now the next thing we have to look at, we'll just write this down. Just kind of circle that. It's important. All right, the next thing we're going to look at is from the top down. So if you're looking down on it, then you have x and y, and then you have this radius that it spins at, that it like moves around at, right? And this here is going to be represented by L sine theta, and then this new angle is phi, and this, we care about this project. So what our x and y values are is this projection, right? So now our new hypotenuse is L sine theta, and so the projection of x is going to be L sine theta sine phi. I'm sorry. Oh, that's our y. Sorry. Of course. So that's our y. And then our x down here is L sine theta cosine phi. And our z, let's just write it again, is L1 minus cosine of theta. So that's what we have to do to start this thing. And then we need to solve the equations of motion, which means we need our Lagrangian. And we'll just remember, so our kinetic energy is 1/2 mv squared, and our potential energy is mgz. All right. So now we have to find x dot, y dot, and z dot. So our x dot, our time derivative of this thing is, we have a product rule. So we have L, the cosine theta, cosine phi, and then theta dot plus L sine theta. Oh, this is a minus. Erase that. It's minus sine theta sine phi, and then phi dot. Beautiful. Okay. Now then our y dot is L cosine theta sine phi theta dot. This time it's plus L sine theta cosine phi phi dot. Great. And then our z dot is just going to be L sine theta dot. There we go. So now we have these. But our kinetic energy 1/2 m x dot squared plus y dot squared plus z dot squared. So that means we got to square these. And that is, it's a lot. So we'll do FOIL, whatever. So we do the first term. Okay, so our x dot squared is L squared cosine squared theta cosine squared phi theta dot squared minus 2 L squared sine theta cosine theta sine phi cosine phi theta dot phi dot, okay, plus L squared sine squared theta sine squared phi dot squared. Okay, great. So this is pretty complicated. There's a lot of terms here. Hopefully things will start to cancel out. And we got our y dot squared, and what's our y dot? Okay, so y dot squared, we'll keep that in view here. That's going to be L squared cosine squared theta sine squared phi theta dot squared plus twice L squared sine theta cosine theta sine phi cosine phi theta dot phi dot. Good. And then plus L squared sine squared theta cosine squared phi dot v dot squared. Okay, and then you can already see the good news is that this here cancels out with this one. So that's good. So we're off to a good start. Z dot squared is just L squared sine squared theta dot squared. That's all. All right, so that's pretty simple. Now we have to add them all together. And when we do that, first let's see if we can like simplify all of these. So let's just rewrite it really quick. So we have x dot squared equals, so I'm just going to rewrite it here, L squared cosine squared theta phi theta dot squared plus, oh, I put theta phi, that's not right. There we go. So this is cosine squared phi theta dot squared. Sorry about that. Plus L squared sine squared theta sine squared phi dot squared. Then y dot squared equals L squared cosine squared theta sine squared phi whatever, phi full theta dot squared plus L squared sine squared theta cosine squared phi dot squared dot here. Okay, so there's all kinds of identities when I was first looking at this, and then I realized just the Pythagorean identity is the one that works here. So what we're going to do is just in this bottom one on y, we're going to turn these here. I'm going to change color so it's easier to see. We're going to turn this sign into cosine. So we get L squared let's just put the theta dot squared here, and then we get cosine squared theta, and then 1 minus cosine squared phi, and then we'll do the same thing. We'll turn these into sines, so then L squared phi dot squared sine squared theta, and then 1 minus sine squared phi. There we go. Now, if we expand that, we'll have this this term here. With this term, we get a L squared theta dot squared cosine squared theta. This is a minus cosine squared phi. And you can see this term cancels out with this first term in the x dot. So that all goes away. And we're left with L squared theta dot squared cosine squared theta. And then the same thing here. So we're going to have minus, so we have this term and then minus L squared phi dot squared sine squared theta sine squared phi. This cancels out with this term. So these two go away. So then we're left with plus L squared phi dot squared sine theta, sine squared theta. All right, great. And then we just have to add our z, which was L squared sine squared. Okay, so plus L squared sine squared theta, sine squared theta, theta dot squared. So L squared theta, theta dot squared cosine. So you can see these two now we can combine. So we'll write this whole thing now. We have, let's change color again. Keep things interesting. Okay. So we get our kinetic energy is 1/2 m, and then we'll pull out an L squared, and we're going to get, so cosine squared plus sine squared equals 1, so then we're going to get theta dot squared plus L squared phi dot squared sine squared theta. And that is our kinetic energy. Whew, okay. And then remember our potential energy was mgl 1 minus cosine theta. Great. So now we've got our kinetic and potential energies. We just have to do our Lagrangian. So our full Lagrangian is 1/2 ml squared theta dot squared plus, oh, I pulled out this L squared, sorry about that, plus phi dot squared sine squared theta minus mgl 1 minus cosine theta. Great. So we're ready to do our equations of motion. We are there. So we just have to write this out. We'll do theta. So there are two variables. Our independent variables are theta and phi. So we'll start with theta. So d dt of partial L with respect to theta minus partial L with respect to, theta dot, excuse me, respect to theta equals 0. And so we'll do the partial L with respect to theta dot first. All right, and what is that? So we get a twice of a half, so we get 1 ml squared theta dot, right? There's no other theta dots anywhere hiding? No, okay, good. So then our time derivative of that guy, of this theta dot, is going to be ml squared theta double dot, right? Am I missing anything? No, I don't think so. Okay. So that's good. That's for our theta, right? Okay, now we need to do this part. Partial L with respect to theta. And so we've got a theta here and a theta here. Okay, so the first one we're going to get a 2 times, so 1/2, 2 times a half, so ml squared. And then sine theta cosine, because the chain rule, right? Cosine theta. And then minus a minus is a plus, but then you get another minus. So just to highlight that. So minus, minus, but the derivative of cosine is minus sign again. So we get minus sine, or mgl, excuse me, mgl sine theta, and I believe that's it. Yeah. that now we have to write, now we got to combine them. So we are subtracting this entire thing from this. So we get ml squared theta double dot minus ml squared sine theta cosine theta plus minus minus again mgl sine theta. Great. So we can divide everything to get this double derivative term alone. So we divide ml squared, and we're going to get theta double dot, and we'll put everything on the other side just right away, equals ml squared goes away. This is now a plus sine theta cosine theta. I'm missing any terms here. I dropped something? Yes, I did. So sorry. There's a phi dot squared that I dropped here. Yeah, okay. Phi dot, you gotta be careful with these. Phi dot squared minus g over L now sine theta. And I believe this is our final equation of motion in regards to theta. And it's interesting to notice if you let phi go to 0, then you have just your normal pendulum. So it makes sense. Cool. Now we're going to do our phi term. So we have d dt of partial L respect to phi dot minus partial Lagrangian with respect to phi that equals 0. All right, and so differentiating this, let's take our Lagrangian again. See if I can move this. Well, let me move this whole thing. Yeah, I can. Oh. Let's move this down here. Okay, great. Just so I can see it. All right, so now our partial of our Lagrangian with respect to phi dot. All right, so where's our phi dot? It's here. And that's it. So we only got one. So we got a 2 and a 2 again. So we got ml squared phi dot. Okay, and then that's attached to a sine squared theta. So you have to be careful here when you're taking the time derivative of this, which is what we're going to do now, that you do it correctly. Because there's a chain rule, product rule, and stuff. All right, so that means we have this ml squared up front, and we have phi double dot attached to a sine squared theta plus two times phi dot normal, and then sine theta, and then chain rule again, cosine theta, with a theta dot at the end of it for chain rule. And then that, and then this here, so finally, partial L with respect to normal phi equals 0 because there are none here. So we get this expression only equal to 0. And we can actually divide an ml squared and also 1 sine theta. And that's going to get us sine theta phi double dot sorry about that, and then equals minus 2 cosine theta phi dot theta dot. And that is it.